Now we have Andy Rivkin, John Hopkins, and his title is How many CH class EOs can we expect, or do we expect?
All right. Thank you, Mara. Thanks for having this session. Thanks, everyone, for coming. Hello, everyone out there in streaming internet land. So I'm going to have kind of the same kind of content as Martin, keeping with the water theme. I guess maybe I'm looking at it as more of a glass half full than a glass half empty, as it turns out, and coming from a different direction slightly. So we've all heard a lot of motivation as to why we want to do this, kind of figure out how many objects out there are mineable. There is a lot of graphics out on the internet. I'm not saying this is right or wrong, but people are coming up with values for asteroids that are astronomical. And obviously we want to try to root these numbers in something that's more defensible. And there's also a lot of great science to be done. How much water's out there and how much water was delivered to the terrestrial planets, for instance, is an interesting science question. So Martin mentioned the 0.7 micron band. I'm going to go into this a little bit more. These are two meteorite spectra. They both have an absorption band here at 3 microns. This is due to OH and water. This is really what you want to see on an asteroid if you're going to mine water. But this is a very difficult part of the spectral, the electromagnetic spectrum to work in. There are not many telescopes that cover it. The atmosphere is in the way. It's a very tough place to work. So instead, a place that's easy to work is here in the visible, and this band is an easy thing, relatively speaking, to observe. But it's not in every object that has a 3 micron band. So when you see this, you get this one, but the reverse is not true. Still, there's a lot of data on this spectral region, so for our purposes here, we're just going to look at that. CH asteroids, those are the ones with that band. So when I talk about CH asteroids, they're the ones that have this band, so we know they have the 3 micron band. There's some evidence that this type of asteroid is associated with the CM carbonaceous chondrites specifically, which is also good because those seem to fit the bill in terms of mining water. This is kind of going to be a lower limit on the number of hydrated asteroids because, like I said, some that have this band don't have this band. Given all these uncertainties, I'm going to try to keep this to one significant digit. So I'm not going to talk about lots and lots of precision. We're just going to look statistically, what do we think might be out there roughly. Some previous work, Martin just talked all about his previous work and some of the papers that have been done. He took a somewhat different approach. I think the numbers are grossly similar, even though I admit I didn't take as much time as I might have to compare exactly how the approaches were the same or different. I think Martin had a factor for economic viability that we are not using here. So we can look at the supply side, so to speak. We know, or at least we have models of the NEO delivery from the main belt. And Bill Botke et al. Looked and came up with various fractions, various parts of the main asteroid belt that deliver material to the NEOs. We have in different parts of the asteroid belt where the right kinds of, the fraction of the right kind of asteroid. In the inner belt, you have as much as 35% of asteroids in the inner main belt are low albedo carbonaceous material. Going out to larger numbers in the outer belt, we have measurements or estimates of what fraction of these low albedo asteroids have the 0.7 micron band. I've done some of that work. Sonia Fonacier, who's here at the meeting, I think, has done a different one. So we have at least a reasonable agreement there. You just have to multiply this and times that, and you end up with something like 12 to 18% of NEOs should be this type, this CH type. So that's a lot more than you would be led to believe from the meteorites. This is the kind of numbers that Martin was talking about. If you look at meteorite falls, we think this is the least biased of the way to look at meteorites. There have been 45 carbonaceous chondrites that have fallen, been recorded to fall. About a third of them are this CM type, which should be akin to this asteroid group we're talking about. So that's good. That's consistent with kind of this 30% fraction we used on the previous slide. But there's 45 and 16, but there's over 1,100 total. Oh, that should be falls, not fines. I'm sorry. There's 1,150 total. So if you divide this by that, you're only getting 1% CMs in the meteorite collection, 4% carbonaceous chondrites in the meteorite collection. If you look at the larger falls, the numbers are a little bit more, but not a lot more. And these numbers are like an order of magnitude fewer than what you'd predict based on looking at the asteroid delivery. And there are some good reasons to think that the meteorites we collect on the ground are a biased sample. Just most simply, the atmosphere screens out weaker material. And this is part of the reason that there are 2 spacecraft going to carbonaceous chondrite, we think, objects right now, because we don't think we have pieces necessarily of Bennu or Ryugu in the meteorite collection. Interestingly, I don't know if I should go into this too much, there are like 25 meteorites where the orbits have been measured based on seeing the fireball coming in. 8% of those are CM, so that's also a larger number than this. Obviously, this is small number statistics, but it all kind of hangs together-ish. So we've gone from the main asteroid belt and made an estimate. We've looked at the meteorites and made an estimate. We do have some measurements of NEOs. They maybe predictably fall in the middle and have bigger error bars. Scott Stewart and Rick Binzel estimated that the C complex spectral complex is about 10% of the NEO population. They made a debiased estimate of this, so they believe this is a debiased estimate, but there are some uncertainties in albedos of spectral groups that might make this a little less certain. Benoit Carré estimated that something like 23% of NEOs are in the C complex. Wright et al. Estimated that something like a quarter of NEOs have low albedos, so consistent with being C-type. So if you take the 30 to 50% of C complex asteroids being CH, that would suggest that we've got something like 3 to 12% CH asteroids in the NEO population. So again, that's an intermediate number. We can try to reconcile this. Like I said, there are known or suspected mechanisms and processes that can maybe account for this discrepancy between the main belt derived estimate to the meteorite derived estimate. Like I said, there's atmospheric screening might be an issue. Some objects, I think Patrick and Marco Delbo and Simone Marchi have demonstrated that NEO orbits can go through periodic or chaotic epochs of very low perihelion, so they might heat up a lot. That might destroy hydrated minerals at their surface, or at least remove this 0.7 micron band. So again, there's a lot of interesting science to be had figuring this out, and obvious application for people with deeper pockets than mine. Okay, so, I've been up here almost 10 minutes. So if we go with kind of this 3 to 12% CH fraction, which has got big error bars, but is probably about right. We know of about 900 NEOs larger than 1 kilometer, so just naively multiplying, again, the one by the other. That means that we're maybe looking at a few dozen, maybe up to 100 CH asteroids of 1 kilometer in size. If you go down in size in order of magnitude to 100 meters, you probably pick up about 3 times more objects as you get that much smaller. So now we're talking about, again, 75 to 100 CH NEOs of 100 plus meters should be out there. We know of 3? Not many. So this ties into exactly to Martin's point that characterization needs to be done. We might know, we know however many asteroids already. We just don't know which ones are the right ones. We may already have discovered them. Accessibility, this is just a very kind of simple-minded approach that I took. Lance Benner has a page where he lists all the delta V's for every asteroid for rendezvous. There's 3,400 known that are easier to rendezvous with the moon. So again, if you take that 3 to 12% and you just say we're going to assume everything is thoroughly mixed, that would suggest that as many as 400, certainly it suggests at least 100 CH-type asteroids should be easier to rendezvous with than the moon. If you put in the size screen, about a third of them are going to be 100 meters plus. So again, there should be maybe as many as 120, certainly several dozen CH asteroids. So this is, again, the type that you're looking for. Should be easier to reach than the moon. But we haven't identified any of them. Talking about this with Chris Lewicki, he said, well, what about, it's not clear what the correct thing to compare it to is. Maybe you'd really want to compare it to a round trip from the lunar surface, because that's the other place where you might get water. So that ups the delta V considerably, because you have to get down to the surface of the moon, you have to get back off. If you compare it to that, then maybe you're looking at 2.5 times more objects still. So there might be as many as 300 again CH asteroids easier to do a round trip from, or round trip to, than the surface of the moon. There's plenty of caveats, of course. As you can tell, this was, it's an estimate. It's, I think, a reasonably grounded estimate, but it is still an estimate. The major assumption here, I think, is that the NEO population is well mixed with respect to taxonomic types, and that the accessible orbits are also well mixed. I don't know that we necessarily know that. I don't know that if that's, I don't know if we could point to a reason why that's a bad assumption, but I don't think it's been demonstrated. It's not clear how optimistic or pessimistic this is. I think, like I said, hopefully the inaccuracies all balance out. There are, as I noted, far fewer identified CH asteroids than you might expect. We haven't done a student's t-test or anything to see if that's significant. But again, we're looking at this specific case of a subset of hydrated asteroids, so that'll help. We're looking at a conservative case. And I think part of this is that there's really been a dearth of visible wavelength measurements of asteroids. People moved on and looked mostly in the near infrared from 1 to 2.5 microns, because that's where science drove us. And so when you're out there, you can't see this absorption band, so we haven't been measuring that a lot. I know the NeoShield 2 database is either about to be published or has just been. And that, I think, will give us a lot more information. As noted, the Gaia database will give us a lot more spectra. And of course, there'll be call for new observations. So I think I'll just skip to the Twitter-friendly conclusions. NEO delivery models suggest that maybe there's a factor of 10 discrepancy between the number of hydrated or CH-type asteroids than meteorite falls would suggest. We think, at least simple-mindedly, that as much as 12% of NEOs should be in this CH class. Statistically speaking, at least 75 currently known asteroids of 100-meter diameter should be both CH class and more accessible than the lunar surface. Put an asterisk there because should is kind of a funny word to use, and there's a lot hidden under the hood. And then ongoing surveys might identify some of these objects, but we might need a dedicated observing program to identify these. The asterisk here is that there are other ways to identify hydrated asteroids. Looking for this band and this particular type may or may not be the best way to do it, but at least this, I think, gives us a ballpark estimate of what's out there. Thank you.
I'm wondering if maybe we should give more time to. Okay, you have 1 minute, and I think the next speakers. To answer questions, I think we want to give more time to the speakers because we keep running out of time from the question and answer. So, any questions right now? We won't have a lot of time.
They're all baffled.
It's like, too much statistics.
Yeah.